My name is Jennifer Taggart, and I'll be talking about space radiation effects in CB-RAM resistant memory. Before I get into my presentation, there's a few acronyms that will pop up throughout. So one of them is CB-RAM, which is conductive bridging random access memory, TID, which is total ionizing dose, DD, which is displacement damage, and I'll also refer to it as displacement damage dose, NEAL, which is non-ionizing energy loss, LET, which is linear energy transfer, redox, which is short for oxidation and reduction reactions, and SHRIM, which is a simulation software for dealing with heavy ions, and it stands for stopping and ranging of ions and matter. So the motivation for my work is to understand how these CB-RAM devices work in a high radiation environment, such that you might find around Jupiter and its moons, which, as far as NASA is concerned, one of their upcoming missions is the Europa Clipper mission, which will essentially have to withstand, the electronics within the satellite are going to have to withstand a very high and intense radiation environment and need to withstand 10 megarad or above of exposure to high energy electrons. And so I'll get a little bit more into that after this slide. But I'm also going to cover how CB-RAM devices work, how I make them, how I test them, and then get into the radiation effects during retention of state tests, DC cycling, and pulsed programming, more oriented towards neuromorphic pulse tests. And then lastly, I'll start to discuss how the effects that we observe during those electrical tests correspond to material changes that we see and the mechanisms that are causing those the observable radiation effects. So there are different types of radiation. There is ionizing radiation, which are charged particles or photons. And so charged particles are actually what's called directly ionizing. And so that means that the ion that has some kind of positive charge or a negative charge is going to be essentially shot through the material. And so its charge will interact through Coulomb forces on the electrons in the material, transferring energy to those electrons and causing them to be essentially ripped off of their atom and become free. For photons, it's actually considered direct ionizing. So these are like gamma rays, X-rays, and this is because essentially the photon first has to be absorbed by an electron before the electron can be ejected off of its atom. And so depending on the energy of the photon, there's 3 different mechanisms for this free electron or generation of charge. And so you have the photoelectric effect, which is for low energy under a few hundred keV photons. There's Compton scattering, which is about a few hundred keV up to 1 MeV. And then above 1.5 MeV, you have pair production that can occur that will cause a generation of charge. And then besides ionizing radiation, there's also displacement damage. And so once these charged particles start to range out, meaning they've lost enough energy that they're no longer interacting with the matter around it through Coulomb forces, they're actually becoming more ballistic. So there's you'll have kinetic elastic scattering and inelastic scattering. So meaning that essentially the particles will slam into an atom, and then that atom in the material can either absorb some of the energy and stay in place, so you'll have a transfer to phonons, or that essentially that atom absorbs enough energy to be ejected out of its placement in that material, and then it scatters elsewhere. And so it now has kinetic mass and can cause a cascade of damage throughout the material, in addition to whatever energy your initial ion has as well, because it can continue to go on and create an additional damage path. And then in addition to these ranged out heavy ions, you also have neutrons. And so neutrons, they don't interact through Coulomb forces because they don't have a charge, they're neutral. So most of their interactions are either nuclear, meaning that they depend, if they're really, really high energy neutrons, they can essentially punch through the nucleus of an atom and knock out neutrons or protons, changing the actual atomic composition. So for example, it's no longer carbon, it's some other element. But then neutrons, if they have low enough energy, it's a very similar interaction to the heavy ions, where they'll transfer that energy and punch that atom somewhere else, causing a cascade of damage. Okay, so this is a picture of Jupiter's southern hemisphere. So these devices, prior studies have shown that these devices are pretty hard to a TID of about 10 megarad and possibly higher. And so that's sufficient for Earth's radiation environment. But with future plans to go to Jupiter and other high radiation environments, essentially they're going to have to require that electronics are able to be rad hard up to 10 megarad or 20 megarad to be able to withstand these kind of doses for an extended period of time. So here I have on the left plot a comparison of the electron spectrum for Earth's geoorbit and for the area where Europa is, which is one of Jupiter's moons. And so a future NASA mission is planning on going towards Europa to look for signs of life in the ice that covers the planet. And so scientists are starting to examine this radiation environment and figure out essentially to what levels our electrons need to be rad hard. And so just from this plot, you can tell that for Earth-based radiation, we only have a few MeV electrons, and geo-orbit only go up to maybe about 5 MeV. Whereas for the Europa environment, it's higher than a GeV of energy of electrons. And then not only does it have a wider spread of electron energies, but it's about 16. It's the number of high energy electrons in Jupiter's magnetosphere is about 6 times that of Earth's. And then this chart on the right here, this shows a comparison of the dose that would be received for various thicknesses in shielding. So essentially the satellites, they have shielding around the electronics to help try to mitigate some of these TID effects. But the thing is that the thicker your shielding, the heavier the instrument or the satellite's going to be. So ideally you want these shields to be as thin as possible. But so they have a comparison of 3 different materials, so aluminum, tungsten, and some combination of aluminum and tungsten. And as you can see, even for a pretty thick shield, you're still at 10 kilorad of dose just for only 30 days in that environment. So for comparison, for Earth's geo-orbit, you can spend 10 years in that orbit and only get a few hundred kilorad, whereas you're getting for the range of shields projected for this study, it's 10 kilorad just for 30 days, and if you go to a thinner shield, you can go up to hundreds of kilorad in that 30-day time period. So it's not essentially things have to be much, much harder. So megarad hard versus a few hundred kilorad hard, like for the Earth environment. And this dose is mostly due to the high energy electrons, like I show in this left plot, in this environment, in addition to some heavy ions such as oxygen, sulfur, and protons, especially near Europa's closer to Europa's surface. Okay, so next I'm going to get into what a CB-RAM device is, how I fabricate it, and how I characterize and test it. Okay, so here we have our standard cell. We've got an anode of silver, which is an active metal, easily ionizable. We have germanium selenide doped with silver, which that doping turns that chalcogenide glass into an ionic electrolyte. And then we have a nickel cathode. And whenever we apply a positive bias to the anode, you oxidize the silver, meaning it loses an electron, and so now you have a positively charged silver ion, and it will migrate along the applied electric field to the cathode, which is the nickel contact, where it gains an electron and reduces, becoming metallic silver again. And so at that point, that atom electroplates under the nickel cathode, the electric field becomes that much, just a slight bit stronger at that point. And so the rest of the ion supply is going to be directed towards this plating of silver to the point where you have this filament that grows from the cathode up to the anode. And when you reverse the bias, you can reverse that redox reaction. So essentially, here's that same diagram again. So as that bias is applied, this filament will go from the cathode to the anode. Once the cathode and anode are connected by this conductive filament, then the device is effectively in a low resistance state. You can continue to apply that bias and bulk up that filament to go to an even lower resistance state. And then when you want to erase the state, you just simply reverse the bias and you reverse these oxidation and reduction reactions. Okay, so next I'm going to get into the fabrication of the CB-RAM devices. So first we start with a silicon wafer, and we deposit about 100 nanometers of SiO2 on top just to isolate the silicon from the rest of the devices. Next, we do e-beam evaporation of nickel to about 65 nanometers, and then we will pattern that using contact lithography and wet etch that to get the cathode bars. So that's these going into the screen here. And then next we'll deposit more SiO2 to create an isolation between the devices. And then we'll pattern that again with contact lithography. So you see these are the areas where it gets developed. And then we'll wet etch that in order to get vias that go down to the nickel layer. And then these are also the vias that are essentially going to hold the material for the actual device. And so to pattern the electrolyte layer, we do a lift-off mask. And so in that case, we develop it such that there is residual resist, essentially where we do not want the chalcogenide to be. And then we do thermal evaporation of the germanium selenide and silver. And then after that, we take it out of the evaporation chamber, put it under a UV light to a certain dose of UV energy, and then that'll drive the silver into the chalcogenide glass. And so that's known as photodoping. And that silver will actually react with the selenide, and then it'll become the fast electrolyte. And then next, we'll dissolve away that the resist and do what's called a lift-off. So it lifts off all that extra material where that was above each of the resist areas. And so all we're left with is these pillars of germanium selenide and silver. Oh, and then we also, before doing the liftoff, we'll actually deposit an additional 35 nanometers of silver to act as a supply for the programming of the devices. And then so here, this bottom figure shows a finished cross-section of a crossbar array. So the one step I didn't show was the liftoff of this aluminum bar. But essentially, the finished device is this crossbar here, where you have an underlying nickel bar. You have the device here, and you can see that that via where the actual active device area is, and then you have the top aluminum bar that goes across the device area and also helps to protect it in addition to giving it an electrical connection. Okay, so next I'm going to get into how we test these devices electrically. So one of the methods for programming these devices is to do DC cycling, and so that consists of doing a voltage sweep from, say, 0 to 0.5 volts and back, and then, say, 0 to some negative voltage and then back to 0. And then from those characteristics, we can extract important characteristics or parameters such as the programming threshold, the erase threshold, the high resistance state, and the low resistance state. And the low resistance state is actually dictated by a compliance current that we limit using the parameter analyzer. And so as far as what these characteristics correspond to in terms of filament formation, so in this first figure here, once the filament starts to form, you'll see a slight increase in the high resistance state. And then at the moment the anode and cathode short out, you'll see this spike in current, and so that's why we have the current compliance to prevent the filament from overprogramming. But then we can use that compliance to set a specific low resistance state. And then when we reverse the bias, once we get over a certain threshold, then the filament breaks and the redox reaction goes in reverse, and we go back to the high resistance state. Another way of testing these devices is to do retention tests, which is a pretty standard test for any memory technology. So what this entails is you possibly DC cycle it or do pulse programming just to make sure the device works, and then you will use one of those methods to program it into a state, so whether that be a high resistance state or a low resistance state, and then you'll observe that program state over time just to make sure that it can retain that state. Because essentially, if this is a non-volatile memory, you want it to be able to retain that state for years, if not longer. And so I just briefly mentioned pulse programming. So for pulse programming, instead of using an IV sweep to program the device, you're actually using a pulse. So some energy that you apply to the cell that's going to be a product of the pulse width in addition to its amplitude. And so instead of having to necessarily have a compliance current, you're actually controlling that state for how long that pulse is applied. So for example, you might use a very rapid set pulse, so say less than a millisecond. For these devices, you can even go down to nanoseconds to be able to program these devices. But for DC cycling, for pulse cycling, what we do is we'll apply a set voltage, and then we'll do a small DC read, so essentially something that's below the programming threshold, because we don't actually want to disturb the state, we just want to read what the current state is. And then to erase it, we just apply a pulse. It could be longer, it could be the same pulse as the set pulse if you want to keep them uniform, but essentially all we do is we just apply a pulse in the reverse direction. So just apply a negative amplitude pulse. And then again, you do another read in order to get what the erased state is. And so on this figure on the left, so essentially each cycle number corresponds to a set pulse and an erase pulse. And you'll see that you can do this program erase multiple times, and then all of a sudden, at some point, you get some decrease in the high resistance state. And so that gives you clues or a metric in order to quantify how many times you can program these devices before they begin to fail. And an extension of pulse programming, you have what's called neuromorphic programming. And so instead of applying a programming pulse followed by the erase pulse, you apply the same pulse over and over again to essentially modulate the state. And so for neuromorphic, usually you'll use really short pulses compared to, say, like a millisecond or a microsecond to do pulse cycling, and you'll instead be using tens of nanoseconds or 100 nanoseconds, and just you'll incrementally step up that state. So in this case, this is what we call potentiation. So we're programming this, make it go to a lower resistance, so a higher conductance. And then to erase it, we just take that same pulse, reverse the amplitude direction, and then we apply that pulse successively to erase the device. Now that I've explained 3 different ways of testing these devices electrically, I'm going to go over how that corresponds to what we might like to capture during radiation tests. So for retention of state, you essentially, while in a radiation environment, you want to evaluate how well the device can maintain that state throughout the duration of the radiation exposure. And so, for example, if you're in a low resistance state, you want to see if radiation in some way drives that resistance state lower or higher, breaks the filament essentially, or if you're in a high resistance state, like how susceptible is the device to suddenly becoming programmed. For DC cycling, since you get all of those electrical parameters out of doing the IV sweep, so such as the erase threshold, programming threshold, the high resistance state, the low resistance state, you are able to resolve any material changes that would affect the ion migration, so essentially the formation of that filament. You'd be able to capture that in an IV curve because it would essentially distort it in some way. And then as far as pulse programming goes, since you're only applying the voltage for a very short period of time, if there's any changes to the electrolyte layer that might inhibit, say, silver migration, you'll be able to, or change the conductance of the material in general, you'll be able to capture that with the short pulses, because essentially you're only giving a limited amount of time for that ion, for those ions to migrate through the material, unlike with IV switching where you're applying that bias for an extended period of time. You're giving the ions plenty of time to reach the filament. With pulse programming, essentially if the ions cannot get to the filament to help form it within a certain period of time, you're going to fail to form it, and you'll be able to capture that kind of effect using pulse programming. So first I'm going to go over radiation effects that we might see in a retention of state. So for retention of state tests, we did 2 different types of tests. So one of them was a collection of different heavy ions, and then in another test we did Cobalt-60 irradiations. So for the heavy ion tests, this is essentially a combined environment. So this is the heavy ions are supplying both a total ionizing dose in addition to a displacement damage once those ions begin to lose energy. So this plot on the left here, this shows the expected ranging of the ions through the material. So essentially, we have 3 different ions at 3 different starting energies. So we have a lithium at 100 keV, silicon ions at 200 keV, and then tantalum ions at 1 MeV. And so the reason the lithium is tracking through the aluminum layer is because for the lithium ion test, we use the crossbars, which has the aluminum going straight across the actual device area. So for the silicon and the tantalum, as you can see, especially with the tantalum, the ions are already ranging out in the nickel layer and, if not, the SiO2 layer below it. But essentially, if this device had any kind of overlayers, the tantalum would not actually make it into the electrolyte layer. So for these tests, because of the limitation on the energy of the ions, we actually use devices that have this offset aluminum contact. And so the devices still can be probed on aluminum, but it leaves the actual device area open for the exposure of the ions. So therefore, the aluminum layer is not included in their calculation for ion energy loss. So for the lithium and the silicon tests, these were performed at Sandia National Labs using their nanoimplanter, which essentially is a scanning focused ion beam that they can control the beam current on, and so essentially we can raster scan it across the device area and deposit some fluence of ions. And so this is a useful machine because in addition to just being able to pretty precisely raster scan across only the device area, they also have a setup that allows us to track the position of the beam, so we can correlate effects based to the position of the beam, and I'll get to those results later. But for the tantalum ions, we actually use the broad beam configuration at Sandia. So that puts about a 1 millimeter beam on the device, and so obviously the beam's going to be hitting multiple devices. So depending on how small of a die you use, that's not the most ideal setup to use. But for our die, we had pretty big die, and plenty of devices, so we can move around to different devices on a single die without having to worry about overlap from the prior exposure. And so you see this micrograph here. So again, this is the same mask set as what was used for the silicon ions, where you have the aluminum offset from the actual device area. And so for this, it's not a raster scanning source. It just essentially parks a beam over the device area, and then we watch how the state changes on an oscilloscope. So essentially for the tantalum irradiations and one of the silicon irradiations, we actually were applying a 30 millivolt bias the entire time to read the state on an oscilloscope. So here, this is the split of the different energies. So like I said, this is a combined environment. So you have an LET, so this is more of an electrical interaction. And then you also have a non-ionizing energy loss, which is going to be the more kinetic interaction. So you'll have energy loss that doesn't necessarily result in ionizations. It's more of you're punting atoms elsewhere in the material. So for every ion, you have some combination of non-ionizing energy loss in addition to an electrical energy loss, or LET. And so the purpose of evaluating these devices in a combined environment is because you're exposing it to both types of radiation, and we're using multiple ions, it allows us to essentially separate the effects. So I'll get to a plot later, but we want to be able to try to correlate any kind of failures or effects we see due to radiation with the type of radiation, so whether it be TID or displacement damage. And so by having this array of different values, it allows us to try to correlate the effects to either non-ionizing energy loss or LET. And then this plot here shows the vacancies, so essentially this is the interactions that are causing displacement damage. And you can see for the different ions that there's about a factor of 10 difference between each of them. And so that should correspond to these factors between each of them for this this Neal calculation as well. So here are the results for the lithium-ion test and one of the 200 keV set of tests. And so for these tests, these devices were put in the nanoplanar, and so the nanoplanar has an actual probe station inside. So we put it on the chuck, we probe each individual device, and then we'll raster scan the beam over the device. And so what we would do is for these tests, we actually just program the devices, and then we kept them probed, but we did not apply a bias. We hit it with radiation, and then we did a 30 millivolt IV sweep in order to read the state. So you'll see on both of these plots that you have a collection of devices that were programmed into the high resistance state, a few that were programmed into a low resistance state, and then the general trend is you hit some fluence value, and then all of a sudden you see a collapse in the state. So especially for the high resistance state, you'll see the high resistance state all of a sudden floor out to a very, very low resistance. And even for a lot of the low resistance values, for the lithium, you only see one that actually crashed out to an even lower resistance point. But then you do see these fluctuations in the state that kind of correlate to about the same point that you start to see the failures as well. And then for the silicon, same thing. You have several of the low resistance states that drastically change in their state, and then same with the high resistance state. So the changes for the silicon were not as extreme as what was observed in the lithium, though the silicon did have a couple interesting devices, because instead of having a very drastic transition, it was a very slow transition down to the low resistance state. And then here are the tantalum devices, the devices that were exposed to 1 MeV tantalum ions. And so we had two devices that were programmed into a high resistance state and one in a low resistance state. The reason there's so few devices for this data set is essentially this was actually the first ion beam exposure we did. So we didn't know where these thresholds were, especially for this device that was initially in the low resistance state. I ended up stopping before I actually hit the fluence that would cause a state change, mostly because I had stopped assuming it wasn't going to change, and then I incremented the beam to do higher fluence steps, and then I was able to actually resolve that threshold. But yeah, again, for this low resistance one, I didn't realize that I had stopped right before I got to that. But so using the LET that we calculated with SHRM, you'll see on these top axes, so also for the lithium and the silicon, is I'm plotting the fluence value and then the TID equivalent at that fluence. And so for TID, again, this is just in terms of the LET. And then so taking the different LET and NEAL values, so essentially this is how we convert the units, which are actually MeV centimeter squared per gram, and we can convert those to TID, which is in terms of rads. And so you have K, which is a conversion factor going from MeV per gram to rad. And so essentially we take those dEdx values for the LET and the non-ionizing energy loss, multiply it by the fluence of ions and that scale factor, and then that puts both these values into rad units. And so on this plot over here, everything is plotted, both the displacement damage and the TID, in terms of rad for this material, so silver, germanium selenide. And so for the TID values, those are marked by the solid symbols, whereas the equivalent displacement damage dose at that failure for that ion is these open circles here. And so you actually see that changes seem to correlate more with TID values. And so TID, there is some spread, but it's within the same magnitude, minus these outliers out here. This is, again, these are those weird transitions with the silicon that I had mentioned before. But whereas the displacement damage doses are actually spanning over 2 magnitudes of values. So their distributions are a lot more spread out than the TID. So far at this point in testing, it looks like the failures and retention states are actually more due to TID effects than displacement damage effects. So here are another set of tests that were performed using the silicon ions. But with this test, we actually tracked the position of the beam during the scan. So for these tests, we used this circuit down here in the bottom right to essentially bias these devices at 30 millivolts, so we could read their state out on an oscilloscope. And then we also ported that into an ADC on their computer system in order to try to sample the data, the resistive state, in addition to the positional data of the ion beam. Unfortunately, the sampling rate was set incorrectly, so we lost the positional data for the beam. But since every scan is identical, essentially the time that we have is going to correlate. The time during the scan is going to correlate to the same position every single time for each scan. So while I can't necessarily map the resistance to a specific value or specific location on the chip, we can tell when certain effects happen and are able to correlate that to different positions on the die. So backing up a little bit. So for these tests, what we did is we scanned the beam across the device, and while it was biased, we watched the resistive state. And then, so we scanned it across once, and then we scanned it across a second time, and a third, so on and so forth. And so every single time, we see a transition in the resistive state. So all of these tests, we actually started in the high resistance state, and we're watching as every sweep, the resistance decreases during that sweep. And one thing we observed is that a lot of these changes kind of correlated to the same position in the scan, meaning that most likely these transitions are happening at the same point on the device. And so these are 2 different devices that were tested. I think I had a total of 4 or 5 devices that were tested in this way, but these are just 2 examples. So essentially, even on this device 3 here, we see some transitions happening are kind of correlating to the same locations of the dye. And so essentially, what this means is if you have these weak points on the device, so chances are any kind of change in resistance that we're seeing is probably most likely due just to the specific areas of the dye. So chances are that these positions might actually correspond to where a filament already exists in some partial form, because essentially these are all devices that have been IV cycled, so chances are there's residual filament that's trapped in the electrolyte layer that has not fully dissolved, and so whenever the beam scans across it, there becomes a position where it maybe hits the location where the filament is the largest. So when it does that, it's more like almost like a single event effect, where either you have displacement damage effects that are kind of reorienting the silver such that they're now kind of reconfigured so you're filling in the gaps that might have existed, or it could be that you're generating carriers locally around the filament such that with the bias applied, you have the separation of charge, you have a local electric field, and then that would allow for a partial programming of the filament as well. We don't actually know which effect it is, but chances are it's one of those 2, because those would probably be the only 2 methods in order to get this filament to form. So in addition to doing the heavy ion test, we also did Cobalt 60 tests, because Cobalt 60 is a pure TID environment. So if we're assuming that TID is making these sudden changes in the resistance state, then it makes sense to do a pure environment where we can try to see if we can see those same changes. So for the Cobalt 60 test, this was also done at Sandia National Labs at their gamma irradiation facility. So essentially, we were able to get a dose rate of 415 rads of germanium selenide per second. So this correlates to 475 rads silicon per second. So it's a pretty decent dose rate. And so what we did is we programmed these devices into either the high resistance state or a low resistance state, and then we hooked these up to an oscilloscope and applied, I believe it was a 50 millivolt bias. I'm using this circuit down here. And so we essentially were observing the state of these devices for the entirety of the radiation exposure. And so this exposure took about 12 hours to complete. So this is all done and also in one dose step. So we're just observing these effects in situ. And so for the entirety of the exposure, we got up to about 23.9 megarad of dose in this material system. So it's right in the region is where we started to see effects for the heavy ion test, but it wasn't actually at about the mean threshold. So ideally, we would have liked to have gone longer. Unfortunately, we didn't have the time on the source to be able to do that. So, but as far as the results go, with the low resistance state, we didn't really see any kind of change in state. The devices were extremely stable. But for the high resistance state, we did see some drift, but there was no sudden failure to a low resistance state like we saw with the heavy ion data. So as far as like a binary state consideration, there was no failures of state. They either stayed in a high resistance state of some sort or in a low resistance state. Okay, so next I'm going to go into DC cycling and the effects that we see due to radiation during those types of tests. And so for these tests, we used both heavy ions, again, the same, in this case it was lithium, and then we also used the 14 MeV neutrons for a displacement damage environment. So for these exposures, what we did is we used the 100 keV lithium with the nano implanter. And then instead of doing retention tests, what we were doing is IV sweeps between each fluent step. So essentially what we would do is we'd cycle the device. We would do a DC read to see its resistive state. Then we would hit it with a scan of the ion beam, and then again do a DC read afterwards, another IV sweep, a DC read to get the state again before then hitting it with another dose of radiation. And so essentially we just kept doing that pattern of read, cycle, read, expose, read, cycle, read, expose. And so from the IV sweeps, so here this plot on the left, this gives you an example of an IV sweep of one of the devices. We sample the high resistance state and the low resistance state as the 30 millivolt point, and use that as the resistance values over here on this plot on the right for the low resistance value and the high resistance value during that sweep. And so the red is one device, and then the black icons are another device as well. And so these are the two devices that were tested. And so one of the interesting things we saw in this behavior is essentially we get to some fluence value, so around 6 or 7 E12 per centimeter squared. And you see that both the low resistance state and the high resistance state of both devices started to increase. The window between the states is about the same, but both the low resistance state and the high resistance state again increased. But as you can see with the two control devices, as you saw, we see no kind of fluctuation. The controls were able to hold their state for the duration of all the cycles. Okay, so now next we're going to look at this effect here and see what is going on with the actual IV characteristics. And so you see on the plot on the left here, so this is the programming curve. You see for the low resistance state that with increasing fluence, so again, this is starting at the IV sweeps in that gray marked region. And so for the first few sweeps in that region, you see an almost ohmic curve, and then you see it starts to degrade into a less linear curve. And it's it's a pretty ragged response as well. But then if we look at the erase curve, we see, so the ohmic states here for the first few devices, you see that those are pretty linear during the erase sweep. But then for the device 1 and 2, when they start to become nonlinear, during the erase, you do see that linear profile on average. And so what this kind of suggests is essentially that these filaments are partially dissolving. And so this ragged IV profile is actually due to the ions being dissolved away from the filament. And so what we believe is happening is essentially you have this filament that's formed by limiting that compliance current, but the radiation has caused damage to the electrolyte layer in such a way that silver migration is greatly limited. And so essentially the silver that's around the filament will reduce onto the filament, but then you leave like this lag in supply here. So essentially you have this void where it's very silver poor and it's not being supplied fast enough. So essentially when we start to go to the lower voltages during the IV sweep, you reduce the electric field that is between, say, the silver anode and the cathode. And so when you do that, you no longer have a force going down towards the filament, but because of that lag in silver supply, you actually now have a concentration gradient of actual silver. And so diffusive forces, once that field starts to diminish, diffusive forces take over and the filament partially dissolves. So it dissolves enough just to rebalance the gradient of AG population, and then so you're left with a smaller filament or thinner filament than what you intended on programming. Okay, and so for these tests, we looked at, in addition to that gray area where we had those interesting effects there, both of those devices collapsed in their programming window. So essentially the high resistance state fell to the low resistance state. And so we're going to go ahead and mark those fluences on this plot from before, And you notice that these are about the same area as a failure as far as fluence goes as we observed during the retention test. So whatever these effects are, they seem that that's causing this failure in state, they seem to be correlated with the fluence. And so next we continue on with neutron tests. So essentially this is a displacement damage environment with very little TID in comparison. So for in silicon, you'll have maybe 100 kilorad worth of dose due to a secondary ionization in this process. But the majority of damage, or the dose received, is going to be a displacement damage dose, so non-ionizing. And so here's 3 different devices that we tested. We tested a total of 5 of them in this manner. So again, for these tests, we did a fluence step of neutrons, and then we did a set of IV sweeps, and then hit it again, and then IV sweeps, and so on and so forth. And so for these tests, since we were working with higher fluence steps, I was actually able to I did 5 IV sweeps between each fluence step. For the prior test, since I was gradually stepping up the fluence, I only did 1 IV sweep, so that way we could, if we did see changes, we knew that it was due to radiation and not to wear out of the device, because doing the IV sweeps puts a lot of energy into these devices and can cause material damage over time due to joule heating. So to limit that, we try to limit the number of IV sweeps we do. And so, but even for the neutron test, we do see these abrupt failures in the programming window, just like we did with the ion test. So even though the data for the ion test more correlates to TID effects, we're seeing these same effects with neutrons as well. So this essentially suggests that while TID may be in a combined environment the main culprit for those effects, displacement damage is just as capable of creating these effects as well. The one interesting thing, though, is that for one of these devices, it actually failed into a high resistance state, and instead of all falling to the low resistance state like the ion test did. And so for these tests, it didn't matter how high of a voltage we tried to apply to try to program the device afterwards. We couldn't get that filament to form once it failed into the high resistance state like this. And then, so here's a distribution of all the IV sweeps we performed at each fluence step. So essentially, here's the pre-rad distribution. And so this is with a box plot that has 25 points worth of data. So we've tested 5 devices, 5 sweeps at each step. So 25 devices in each of these distributions, 25 sweeps in each of these distributions. And so this is the ratio between the high resistance state and the low resistance state. So essentially the programming window of these devices. And so you see up until about 2.2 E13 fluence, there's still some distribution between the off state and on state. But once you get to 2.9 E13, you see a complete collapse. And so essentially all 5 devices are either stuck in a high resistance state or a low resistance state, and there's no variation in the programming window. And so here are that same data, except now it's distributed as CDF plots, cumulative distribution function. So you'll see the red here, this is the pre-rad value. And then you see for each fluence step, you see the resistance distribution starting to decrease. And you see the same thing for the high resistance state. And then you have these 5 sweeps up here, which were that one device, that device 3, that failed to high resistance state instead of low resistance state. Okay, so next I'm going to get into pulsed programming. So in this case, prior studies have already looked at an endurance tests. So for these tests, I'm going to talk about neuromorphic applications. So using shorter pulses than you would for doing standard pulse cycling tests. And instead, we'll do incremental steps up in the conductance, or doing depression-related programming. So essentially, using the same pulse and then slowly erasing the device as well. So here is an example of neuromorphic testing that was performed with the setup at Sandia on these devices that had limited inductance, so we were able to go to pretty fast pulses. So this is the data that from using 100 nanosecond pulses, and I believe we had a voltage of about 0.7 volt amplitude for both the programming and the erase. So essentially, we apply a pulse, and you see a step up in the so this is the erase pulse here first, because this is in terms of resistance and not conductance. But essentially, so you see, starting from a low resistance state, you see a decrease so you see an increase in the resistive state as you're slowly programming it. There is some noise associated, but on average, you essentially are erasing it. And then you get to some point, so in this case, 500 pulses, and then you reverse the amplitude of the pulse, and so now we're programming it to a low resistance state, and then erasing it, and then programming it. And so for this test, we did 10,000 cycles. So again, this is just to kind of show what neuromorphic programming looks like and the ability of these devices. So we're able to, even though this distribution does start to cut off after about 50,000 cycles, you still see some semblance of a window even at 10,000, or 100,000 cycles. Or 100,000 pulses. So for the devices that were actually used for radiation tests, we had these packaged in a dual inline package, or wire bonded, and then placed inside the gamma cell, and then had ribbon cable running out of the gamma cell to the instruments that we're using. So essentially the arbitrary waveform generator and the 4156 for doing the read bias. And because these devices were packaged and the mask set for our crossbars don't have large pads, we're not able to do multi-wire bonds for every contact in order to lower the inductance. And so since we had a lot of inductance, using a higher or faster pulse is going to introduce a lot of ringing into the device. So we have to keep the pulse widths relatively large. So in order to compensate for the width of the pulse, we lower the amplitude. So instead of saying using 0.9 or 0.7 volts for the amplitude, we used 0.5 volts, and we had 10 microsecond pulses. And so instead of being able to also do, say, 5,000 pulses to program it or erase it, I think we're essentially limited to about 10 to 20 pulses for this setup. So essentially, this plot on the left here shows the response of the control devices, and they were equivalent to the essentially the devices that are used for radiation as well. So I don't have that plot on here, but you can see essentially I've marked the control range on this right plot, and so this is the programming range for the control device, and so you can see a pretty big window or a decent window between the low resistance state and the high resistance state, or the potentiation curve and the depression curve. And then even at 16 kilorad, we see a shift down in the distribution of the switching, and then we also start to see kind of a collapse in that programming window. So again, this is Cobalt 60, so this is a pure TID environment. And then at 60 kilorads, we actually start to see, for doing depression, the transition down to a plateaued state is very rapid. So after 1 or 2 pulses, it's kind of staying in that state. But for the potentiation, you see these ragged responses in the ability of trying to program this filament. So what that means is essentially that these pulses are not as effective in forming this filament. And so like I stated before, for doing the DC sweeps, if we're seeing these kind of effects where you essentially have a dissolution of the filament, there's a time lag between when the pulse is applied and when the read bias is applied. And so essentially, like if we try to program this filament, it starts to partially dissolve. It's already in some higher resistance state than what it started initially by the time you apply the read. And so there might be some randomness, some variation in that. So sometimes you might capture it when it's in a lower state or when it's more dissolved. Because again, the timing was based on LabVIEW in the computer, so it's not necessarily as controlled of a time as you would have if you were doing it as a pure pulse train and say reading this out in the oscilloscope. And then also there's some stochastic variation due to the ion movement. So there's going to be a lot of variation in that signal. But essentially this variation and this potentiation, so essentially the ability to program this filament, kind of aligns with what we were seeing with the IV tests, where we have a destruction of the filament or a partial dissolution just because of the ion supply gradient. And so, but granted, this is a pure TID environment, and we're also seeing these effects at much lower values. So instead of seeing these in tens of megarad like you are with ion tests, this is happening at 60 kilorad. And then at 1.3 megarad, we essentially see a complete collapse in the ability to program these devices. So they've gone to a high resistance state, and we're no longer able to program them at all. And so it might seem surprising that these effects are being observed at a lower TID, but actually, if you think about it, essentially with the IV test, you're applying that voltage for a pretty long period of time compared to the time needed to program a standard device at room temperature in a lab setting without radiation. So typically, these devices are expected to form a filament within tens of nanoseconds. And so when you're doing an IV sweep, that bias is applied for maybe 30 seconds, so orders of magnitude higher than what is required to actually program these. But you're actually controlling the current as you're doing this, so you can kind of limit the filament growth during doing a DC sweep. But for pulse testing, you're essentially only giving a small window of time to allow that silver to migrate to the filament. And so therefore, these tests are a little more sensitive to the ion migration, because essentially it's not going to sit there and hold the pulse until it gets enough silver. Like it'll cut off once you get to, in this case, 10 microseconds. And so any silver that hasn't made it to the filament, it's not going to make it, and the filament's going to partially dissolve. So next, I'm going to get into possible mechanisms for radiation damage in this material system. So here is a plot in this inset in this left figure that was taken from one of Mahesh's papers from 2014. And so for this study, he actually used bulk films of germanium selenide doped with silver, and he exposed it to Cobalt 60. And so you'll see for the pre-rad, you have these two distinct peaks here. This is what that's considered an alpha phase, and then this is a higher order silver compound. But essentially, with increasing dose, and so again, this is only at a few kilorad, so this is within the range that we were performing the neuromorphic test. So even after about almost 600 kilorad, we see this creation of what they call a beta phase, and I'll get into what the alpha and beta phase are in just a sec. But essentially, with increasing dose, this alpha phase becomes less prevalent, and the beta phase is shown to have a higher number of counts. So more of the materials transition of the silver selenide nanocrystals within this germanium selenide mixture is turning into a beta phase instead of the alpha phase. And so here I plotted the ratio between the peak of the alpha signal versus the beta. And so you do see as the beta starts to diminish, there's a kind of a trend in that ratio between the two peaks with increasing dose. Okay, and so on the right here we have this is the beta phase here, and then this is the alpha phase. And so essentially, the beta phase is in a bulk silver selenide compound. It's going to be the dominant phase. And so this is silver that's covalently bonded to selenium. This is silver 2 selenide, but it's more of a semiconductor. And then once you get over, say, 300, around I want to say 350 centigrade, you transition to the alpha phase, which is a body-centered cubic with interstitial sites that the silver can loosely bond to. And so essentially this alpha phase is considered a super ion conductor. So it allows the silver to hop from interstitial site to interstitial site, and so it allows for a very large supply of silver ions to migrate through the material very quickly. So this is what makes the germanium selenide doped with silver an actual ion conductor or a true electrolyte. So for the beta phase, since it's a semiconductor, it doesn't really allow ion migration all that efficiently. You can still get ions through, especially through the voids, because it is a glass, so it is an amorphous structure. There are gaps big enough to get the silver ions through and to hop through with different defects throughout the material, but it's not going to be as efficient or as fast as when the material has silver selenide in it. Alpha phase of silver selenide. So this germanium selenide electrolyte is actually, it's a mixture, it's a glass. And so you'll have these nano phases of silver selenide, and then around those nano crystals is you'll have a backbone of germanium bonds, or germanium selenide bonds even. But essentially that backbone puts a lot of pressure on the silver selenide, and so it allows it to exist in this higher temperature state. And then there was one study that actually found that the transition temperature from beta to alpha actually depended on the crystal size. So for nanocrystals, the transition can actually happen at 101 centigrade. And so even then, though, like most of these tests, these are performed in room temperature. And so the fact that these alpha phases even exist are really surprising, but it makes sense when you consider that the germanium also in this material is helping to confine those nanocrystals, put pressure on them to allow them to exist at this higher temperature phase. But if this material is starting to shift from having these mix of alpha phases kind of sprinkled throughout the electrolyte layer more to the beta phase, then essentially we go from having a super ion conductor that can very rapidly supply ions to the filament to something more kind of like how the copper SiO2 devices are, where now it's a slower process. It's more difficult to get those ions to the developing filament. It takes more energy to do so. And so that's something that we're most likely observing when we do the faster pulses for neuromorphic. And again, like I said, for IV tests, is you're applying that bias for a really long time. So you're allowing sufficient time for those ions to migrate to the filament, especially at the lower doses of radiation. So in the cases of doing IV sweeps, it's not until to have a significant amount of dose that your device has been exposed to and that you see those effects. So here is a Mott-Gurney equation, which models ions moving through a material, so essentially ion hopping, ion conductivity. So you have this, so here are my variables here on the right. So you have J, which is the ion current density, and so it's made up of the drift velocity times the charge state of the ion times the concentration of the silver. And so the drift velocity is this function here. So essentially it depends on the thermal velocity, which is the hopping distance times the hopping frequency, as well as these energy terms here. And so once we simplify, essentially we get to this equation down here. And so you have a dependence of E naught, which is the barrier height of hopping, these KT values, and the applied electric field, and again, the concentration of silver and this hopping frequency and distance. And so this thermal velocity is actually dependent on the mass of the ion as well. So it's kind of intrinsic to the ion that's traveling through. So essentially, if say we're comparing how this ion current supply is changing with material changes from, say, going from alpha to beta, for the most part, this barrier height it'll increase, but not significantly. So maybe I think the initial barrier height for the alpha phase is very close to zero, actually, and but can vary to about 0.2 eV. And then even for the beta phase, it's about 0.2 to 0.3. So there's actually not a whole lot of difference in that barrier height for hopping. And if we assume also that between the beta and alpha phase test, that essentially this KT value is going to be static because we're not changing the temperature of the test. We're applying about the same field for both throughout the tests. We're applying the same pulses, the same IV sweeps. So essentially the only terms that are really going to change in this equation from going from, say, alpha to beta is going to be this concentration of silver. So essentially, if we're binding up the silver, the concentration is going to go down significantly. So if the silver concentration goes down, then that's going to drive down the ion current density. So essentially that means that not enough, that the supply of ions is and its ability to move towards the filament is greatly decreased. So again, we have this relation that then the ion current density is going to scale with that concentration. So in conclusion, essentially with both Cobalt 60 tests, with the neuromorphic programming, in addition to other studies on bulk films, we see TID effects. And then as far as displacement damage effects go, for doing the IV sweeps, we see effects due to neutrons. So we see effects due to TID, we see effects due to displacement damage, and in the end, both of these could end up having the same effect on the device. So essentially, with the TID, where we have material evidence of the transition from alpha to beta, but displacement damage can also cause that transition because essentially, if you disturb that germanium background that's putting pressure on those nanocrystals. So if you have some kind of displacement damage that essentially breaks one of those germanium bonds or causes scattering through there you essentially release that pressure on that nanocrystal, and then it transitions from the alpha to the beta phase, which is less conductive. And then for retention of state tests, we went up to about 24 megarad. And we didn't see any kind of abrupt failures like we did in a combined TID displacement damage environment with the heavy ions. And so if we want to actually kind of firmly state whether or not TID by itself can have an effect on more of these DC type of tests, then we would need to go to higher doses of radiation to get that value and see if that's relevant. Unfortunately, I was not able to get to those doses during my work. For pulse programming, we saw these effects due to TID at less than a megarad, which is really surprising because most of the other tests that we've done in the past, mostly have been DC sweeps or pulse endurance tests, which had millisecond pulse times. So they're relatively long. They used compliance limiting circuits instead of actually relying on the pulse width of the test. And so in the past studies, we've never seen any kind of effect due to purely TID. So these effects are very significant because this is the first time we've actually seen these effects electrically, with the CB-RAM being responsive to TID at any kind of exposure below 1 megarad. And then, like I stated, displacement damage, we do see failures with the neutron test. So displacement damage is definitely a mechanism for failure. So in conclusion, essentially, there's no both TID and displacement damage can have an effect on these devices. So it's not necessarily immune to one or the other. It responds to both environments. Though it would seem, based on the heavy ion tests and doing that separation of doses between TID and displacement damage, that actually TID seems to be the most relevant or the most damaging radiation environment for these devices. But again, it's not, at least for doing the the DC type of test, you don't see those changes until you get to around 30 megarad of dose. And so in conclusion, again, these can, depending on how they're used, so essentially if you use them and with slow pulses or do an IV sweep, or use them in such a way where you're only having to read from them so you can retain state, then they're good for a Jovian environment. Unfortunately, if you do want to use them for fast programming for neuromorphic applications, these would not be able to survive a Jovian environment. Okay, so here are my list of papers. And then thank you for listening to my talk.